Okay, well, this is a trigonometry course, so I guess it seems reasonable that at some point we'll study the trigonometric functions. So how are we going to define them here? Well, we're going to use an angle in standard position. So let's let theta be any angle in standard position. Okay, so recall what that means is the initial side of angle theta coincides with the x-axis, and the terminal side is just really anywhere. So here's our theta. All right, now let's let xy be any point on the terminal side of theta. Say right there. Okay, so what we have here is we've got an induced right triangle, and we can label the three sides as follows. This is, of course, x, the horizontal distance. This is, of course, y, giving the coordinate xy right there. And we can also label the hypotenuse as r. Now, by the Pythagorean theorem, we have that r squared is equal to x squared plus y squared. But stipulating that r is always positive, we can actually solve for r by taking the square root of x squared plus y squared. All right, so let me explain what the trigonometric functions are and what they're doing. So trigonometric functions are functions that take an angle as input, and they output one of the ratios of this particular right triangle. So for instance, the sine function takes as input this angle here, and it would output exactly what the ratio of y over r would be. Okay, so sine of this particular angle here, which would be the ratio y divided by r, is a different ratio than, say, sine of this angle here, which is a bigger angle, and the proportions of y and r are different for that angle. Or a smaller angle here, again, giving a different ratio of y over r. So the trigonometric functions do depend on the actual angle that's given in standard position here. Okay, and as they pertain to the ratios of the three sides of this triangle, there are 6 different ways that you can put ratios together. For instance, r over y, r over x, y over r, y over x, x over y, x over r. So therefore, there are 6 different trigonometric functions, and they all have their own names, and we're going to go through them right now. The first one is sine of theta, which is defined to be y divided by r. The next one is cosine of theta, which is defined to be x divided by r. And the next one is tangent of theta, which is defined to be y over x. In this case, we need to stipulate that x is not allowed to equal 0. Now, these 3 are regarded as the principal trigonometric functions. There are 3 more. So those next 3 are cosecant of theta, which is just r over y. Notice it's the reciprocal of sine. Then we have secant of theta, which is r over x. Notice that's the reciprocal of cosine. And finally, we have cotangent of theta, which is x over y. And of course, that's the reciprocal of tangent. Now, these ones also come with stipulations. For instance, y can't be 0 here, x can't be 0 there, y can't be 0 there. So, in other words, the denominator can never be 0. And we don't need to state that for r, because we can always assume that we're choosing the point on the terminal side. So it's r will never be 0. Okay. Also, r can always be determined in terms of x and y, using this formula here. Okay, so those are the definitions of the trigonometric functions. Now, you may have worked with these functions before in a previous math course. Perhaps you took a little trigonometry in high school. And the context that you saw them was probably in terms of triangles. Perhaps you saw that sine of theta was defined as opposite over hypotenuse. But I just want you to look at the way we're defining it using an angle in standard position, which is a little bit more flexible definition than just using physical triangles. But notice that these definitions do agree with what you may have seen in terms of opposite, adjacent, and hypotenuse. Okay, and let's look at some examples now of how we would use these definitions. Okay, so here we're given a theta in standard position. And while we're not actually told the numerical degree value of theta, we do know a point that the terminal side of theta passes through, which will allow us to draw theta. And once we know that, we'll be able to find the values of the 6 trigonometric functions using the definitions that we just worked out. So let's make an attempt to draw our theta. Now the point is in the 4th quadrant. So as we draw axes, we'll just emphasize the 4th quadrant. So the terminal side of theta passes right through that point. So there's the angle theta. And quick side note, sometimes I see students looking at the situation and claiming that theta is in the 2nd quadrant because literally the symbol theta is written in the 2nd quadrant, but I just wrote it there because that's about halfway along the arc for theta. The quadrant of an angle is determined by wherever its terminal side is. So this terminal side is unambiguously in the 4th quadrant, so angle theta is in the 4th quadrant. So we have our x, which is 8. We have our y, which is -6. And we can calculate our r. Well, we know that r is the square root of x squared plus y squared. And x is 8, and y is -6. So that's the square root of 100, which is 10. So r is equal to 10. So now it's just a matter of writing out these 6 definitions. Okay, so sine of theta is defined to be y over r. And we know y is -6 and r is 10. And this fraction reduces to -3/5. Okay. Cosine of theta is x over r, and x was given as 8, and we calculated r to be 10, so 8 over 10 reduces to 4 over 5. Okay, tangent of theta is y over x, so that would be -6 over 8, or -3/4. Okay, cosecant of theta is r over y. So that would be 10 divided by -6, and that's -5/3. If you know sine of theta, which we do, you could also just deduce that cosecant is the reciprocal of that. Secant of theta has the same relationship with cosine, it's just the reciprocal, so we'll know that this answer will be 5/4. But for practice, let's appeal to the definition. Secant of theta is r over x, and r we calculated to be 10, and x was given as 8, so indeed this is 5/4, which is the reciprocal of cosine. And cotangent of theta is x over y, and x was given as 8, and y was given as -6, so this is -4 over 3. And that's it. We have found the 6 trigonometric function values. Let me make a few comments here. The first one is, at no point did we ever really know the degree value of theta. In fact, deducing that from the given information that we have here isn't a straightforward process. However, we didn't need to know the numerical degree value of theta in order to answer this question, obviously. The next thing I want to point out is it doesn't matter where on this terminal side we actually choose the point. We chose the point 8, -6. Well, it was given to us. But we could have chosen, say, this point right here, which is the point 4, -3. That would have given us an x value of 4, a y value of -3, and we would have calculated r to be the square root of 4 squared, which is 16, plus -3 squared, which is 9. So that's the square root of 25, which is 5. So we would have had r equals 5. And building fractions out of those numbers would have given us exactly the same trig function values, as you can see. In fact, we wouldn't have even needed to reduce in that case. So the trig function values really are independent of the actual point that we choose, as long as that point is on the terminal side of theta. And finally, I'd like to draw your attention to the fact that some of our answers were negative and some of them were positive. That is a particular mechanic that we're going to deal very closely with throughout the semester. If you know that theta is in the 4th quadrant, as it is in this case, you could predict in advance that the cosine and the secant value would be positive and all the other ones will be negative. In fact, in the next lecture, we're going to go through exactly how you can do that. Okay, so here we're given the equation of a line. So let's sketch the graph of that line and see what we can work with. Okay, let's write it in slope-intercept form. So that's just solving for y. And if we divide both sides by -2, we get that y is equal to 3 over 2 times x. So we can see that this has a y-intercept of 0, 0, goes to the origin. Good. And this is a line with slope of 3 over 2. All right, well, it goes through the origin, and it has a slope of 3 over 2, which means it has a rise of 3 and a run of 2. So typically that means we would just move 3 units up and 2 units over to find another point, and then draw our line through there. However, we're not going to quite do that in this case because we also had this stipulation in the original problem that x is less than or equal to 0, which means that the entire graph is on the left side of the y-axis. So rather than going up 3 and over 2, we'll go down 3 and over the other way 2 to get this point, and now we'll draw our line through there. Okay, also we can identify the coordinates of that point, which are -2, -3. So we have our xy value given. And our theta in standard position would be that angle there, which we can see is a 3rd quadrant angle. So now we'll just determine the 6 trigonometric values. But wait, we need r first. Okay, let's quickly figure out r. r is the square root of x squared plus y squared. So that's negative 2 squared plus negative 3 squared. So that would be 4 plus 9 under the radical, which means r is the square root of 13. Okay, so now let's figure out the 6 trig functions of theta using the definitions. Sine of theta is y over r. And we chose our y to be negative 3, so this is negative 3 over r, which is rad 13. Now we should rationalize our denominators. So we'll multiply the top and the bottom by rad 13, giving us a sine value of negative 3 rad 13 over 13. Okay, cosine of theta is x over r, and x is negative 2, so this is negative 2 over rad 13. And again, rationalizing will give us negative 2 rad 13 over 13. All right. Tangent of theta is y over x, which is negative 3 over negative 2, and the negatives cancel, giving us positive 3/2. Cosecant of theta is r over y, so that would be rad 13 over negative 3. All right, now it's okay to leave a negative in the denominator, but I usually try to avoid that. So you can move the negative to the numerator, as we have in the sine and cosine case here, or you can just put the negative in front of the fraction. So we have negative rad 13 over 3, and I think that looks a little cleaner. Okay, next is secant of theta, which is r over x. So that would be rad 13 divided by our x value, which was negative 2. And again, we'll write that as negative rad 13 over 2. And finally, that's cotangent of theta, which is x over y. And x is negative 2 and y is negative 3, so the negatives cancel, giving us 2/3. And there we are. We have the 6 trigonometric functions of theta. And once again, we don't know the actual numerical degree value of theta, but it wasn't necessary for solving this problem. And I really want to point out that we didn't really even need to graph it. We didn't even need to graph the last one in the last example. In the last example, with x equal 8 and y equal negative 6, we could have just found our r, and then we would have had our x, y, and r, and gone directly into the definitions without sketching anything. In this one, we also didn't need to sketch. We could have just consulted this equation here, and noting that x had to be negative, choosing our favorite x value. So for instance, choosing x equal negative 2 would be a good choice because it would cancel with the denominator, giving y equals negative 3 as a corresponding y. Then armed with our x and our y value, we calculate our r value, and then we go directly into the definitions and we don't have to do any graphing at all. We've only been graphing while solving these ones just to give a little visual context. All right, while we're still lacking a way of truly evaluating trigonometric functions at any old specific angle we're given without knowing an xy coordinate, what we can do is actually, using the definitions so far, we can evaluate trig functions at quadrantal angles. So remember, a quadrantal angle is just an angle that coincides with one of the axes in standard position. So for instance, that would be like 0 degrees, 90 degrees, 180 degrees, 270 degrees. But also they keep going around forever. For instance, on the right here, we also have 360 degrees. And again, if we keep going, we have, say, 450 degrees just by adding 90. So basically, any multiple of 90 degrees is going to land on a quadrantal value. Now, the reason we can evaluate those ones is because we can easily pick points on an axis and work out the trig function values from the x, y, and the r. So for example, if we wanted the sine of, say, 90 degrees, well, what we do is we draw 90 degrees in standard position. Okay, so we know that's right here. Then select any point you want that's on the terminal side. For instance, we could go with 0, 17. Okay, we have selected x equals 0, y equals 17, and we can calculate that r is the square root of course, x squared plus y squared, which would be 0 squared plus 17 squared. And without doing the whole arithmetic, we would just get the square root of 17 squared, which is 17. So here, r is equal to 17. Okay. Returning to the original problem, sine of 90 degrees would be, by definition, y over r. And we chose our y value to be 17, and we calculated an r value to be 17. So 17 over 17 is 1. So the sine of 90 degrees is indeed 1. Okay, now first of all, note that this is really independent of whatever point we choose. We went with 0, 17, but if we'd gone with 0, 5, then our y would be 5, and our r would also just turn out to be 5, so we'd have 5 over 5. Okay, and I'd also like to point out that the fact that sine of 90 degrees is equal to 1 is an absolute fact. That's not a contextual result based on a particular problem that we're working out. That's an actual fact. If you go to a calculator and ask it, what is the sine of 90 degrees, then you can see that the answer is 1, as we worked out. Note that if you're not in degree mode, if you're in radian mode, which we're going to work with, again, for most of the course, but not until chapter 3, the process is a little different and we get the wrong answer here. So make sure that whatever calculator you're using for now is in degree mode. All right, let's look at another one. Cosecant of 270 degrees. So, okay, let's draw 270 degrees in standard position. So we know 270 degrees points this way. So we can pick our favorite point on that line. And this time, why don't we choose some easy numbers to work with, like 0, -1, rather than going all the way to 17. So we have x is equal to 0, y is equal to -1, and we can calculate our r value, which is x squared plus y squared, and so that's the square root of 1, which is 1. Okay, r is actually really easy for a quadrantal angle. It's always just going to turn out to be the absolute value of whichever x or y is not 0. So in this case, it's the absolute value of -1. In the last case, it was the absolute value of 17, which is 17. Now we can say that cosecant of 270 degrees is defined to be r over y, and that would be 1 over -1, which is -1. So cosecant of 270 degrees is -1. And let's confirm that on a calculator. Now your calculator might not have a cosecant button, but we know that cosecant is the reciprocal of sine, so I'm going to go 1 divided by sine of 270 degrees. And indeed, we do get an answer of -1. All right, let's try cosine of -450 degrees. Now, this one here is outside the interval that we're comfortable with, which is the 0 to 360 interval. So let's find the least positive angle coterminal to -450. Okay, that's a skill from the first lecture. And what we're going to do is just continue to add 360 degrees until we get something positive. So if we do this once, we'll get negative 90, and we can do it one more time, and that'll get us 270 degrees. So there is negative 450. And actually drawing the angle, we'd have to draw this clockwise because it's a negative angle, and it goes around a whole time and then stops there. So there's our theta. All right, so we'll pick our favorite point on there, which this is actually the same point we chose for the last problem, 0, negative 1. So we can see that x is equal to 0, y is equal to negative 1, and r will turn out to be 1. Okay, it's just that positive distance. And now we can evaluate cosine of negative 450 degrees. So cosine is defined to be x divided by r. So in this case, that would be 0 over 1. So cosine of negative 450 degrees is 0. All right, let's check cosine negative 450. And indeed, we get 0. And I'd like to point out that actually, trig function values are preserved through coterminal angles. So remember, this was also coterminal to negative 90, and we still get 0. And it was coterminal to 270, and we still get 0, of course. When you are working these out on your homework, it is very important to avoid using a calculator to get these numbers, okay? So don't deny yourself the opportunity to be practicing working these out without a calculator. All right, let's do another one. How about cotangent of 0 degrees? All right, well, let's draw 0 degrees in standard position. So 0 degrees is right here. And we'll pick our favorite point along there. So how about 1, 0? Which means that we are choosing x to equal 1, y to equal 0, and r to be 1, which is the square root of 0 squared plus 1 squared. So cotangent of 0 degrees is defined to be x over y, and that's 1 over 0. Uh-oh. That's a problem. Remember, this definition only applies if y is non-zero. All right, but here we do have y equals 0. So now what? It's not a huge problem. We just simply say that the cotangent of 0 is undefined. And there it is. All right, I'd like to make a quick remark on notation here. Frequently, we're going to be writing more complex trigonometric expressions that just involve one or more trig functions, and those trig functions will be squared and cubed and raised to various powers. So for notational convenience, if you see something like this, sine squared of theta, it means sine of theta as a quantity that's being squared. So you work out sine of theta and then you square it. Okay, so for instance, recall cosecant of 270 degrees we worked out as negative 1. Therefore, cosecant squared of 270 degrees, which is the square of cosecant of 270 degrees, is equal to the square of what cosecant of 270 degrees worked out to, which was negative 1. And so cosecant squared of 270 degrees is equal to 1. So as our final example, let's evaluate cosecant squared of 270 degrees plus 4 times the sine of 90 degrees. All right, well, This one again is the square of cosecant of 270 degrees plus 4 times the sine of 90 degrees. And that would be -1 quantity squared plus 4 times. We evaluated sine of 90 degrees a while ago, and we got an answer of 1. So this would be 1 plus 4, which is 5. All right.